Hello and welcome to the final lesson of waves. This is D2 lesson 4, the Doppler effect. So in this topic, we're going to be talking about what happens when the source of a wave is moving relative to someone who is observing the wave. So for example, did you ever notice that when a motorcycle zooms by you on the highway, the sound that you hear as it's approaching you versus the sound that you hear when it's moving away from you are actually different. You aren't just imagining that they sound different. Same thing happens if you've got a train zooming by you and it's blowing its whistle. The sound of that whistle as it's going towards you is going to be different than the sound going away from you. And the reason for this is what we call the Doppler effect, and it explains what happens when the source of a wave is moving relative to an observer who is sensing the waves. Here in Physics 20, we aren't going to be dealing with observers that are also moving. So in this case, it's just going to be the source that is moving. And most of the time, that source is going to be creating sound waves here in Physics 20. The Doppler effect is also quite important when you are talking about astronomy. Sometimes you talk about red or blue shifts. We aren't going to get into that too deep here, but just know that this Doppler effect does have applications outside of sound. Okay, so like I mentioned, the Doppler effect is all about when the source of sound waves or light waves is moving relative to an observer. So in this little simulation here, and I'll post a link to where this is if anyone wants to go and play with it themselves, we have these little sliders that let us change how fast the source is going to be moving to the right. And we can also play with the observer's velocity. Like I said, we aren't going to worry about that right now. When I press start, what's going to happen is that the source is going to start emitting waves around it. I'll just demonstrate here. So you can see we've got these waves around here where the green line represents a crest and the middle of the space in between represents a trough. So we're looking at waves from above this time, sort of in 2 dimensions. And what you can see, so since the source is not moving and the frequency of the waves that the source is emitting is constant, if we press start again here, or just resume it, there we go, you can see that the distance between the crest, which of course we call the wavelength, is constant the whole way through. I'm just going to show what happens if instead we start the source moving to the right with some speed, let's say 130 meters per second. Obviously this is simulation, it's not actually going to be moving at that speed. And take a look at what the wave diagram looks like in this case. And we will pause it here as well. So I'm going to explain these on the other document where I can write and stuff, but just keep in mind what is happening here with this. Okay, so I've got the other document up here where I can draw on it. And so in this one, we've got that this source here is moving to the right at a velocity, in this case, of 99 meters per second. The observer here is stationary. And if you look at the pattern of waves here, so again, these green lines represent crests, and the white in between would represent the trough. So remember that the distance from one crest to another is equal to the wavelength, or lambda. And so right away we can see that the wavelength that occurs over here to the right in the direction that the source is moving is smaller than the wavelength to the left. So over here we've got a wavelength as well, but obviously these 2 wavelengths are not equal to each other. And the reason that this happens is that as the source moves, sort of the origin of each wave pulse is from wherever the source was at the time that it was released, but because the source is moving, it sort of looks like the circles are moving to the right. And so over here on the right, we end up with some compressed wave pulses, whereas over on the right, we sort of have an expansion between pulses. And so the outcome of this is that if we have a shorter wavelength, well, because our velocity of the sound in this case is going to be constant. Remember, velocity is equal to frequency times wavelength. So if the wavelength goes up, this means that the frequency has to go down. And similarly, if the wavelength goes down, the frequency has to go up. In this case, the wavelength has gone down, so the wave pulses are closer together, so our frequency is going up. So the apparent frequency of the waves is actually higher than the frequency at the source. So what this means is if you are listening to something that is approaching you, the frequency is going to appear to be higher than it would be if the object was just stationary. So we've just got that again mentioned here, that the frequency that is apparent is higher than the source. If the object is moving away from you, so again we've got the source is moving to the right here, so it's moving past us, we can see that this wavelength again here is not equal to the wavelength over on the side. And you can see that this wavelength has gotten bigger. And so anytime we have a longer wavelength, we get a lower frequency. And so in this case, the frequency that we hear is going to sound at a lower pitch than it had otherwise. The actual magnitude of this change in frequency is not too tricky to calculate. We've got this formula here that's also found on your formula sheet in the section about waves, in which case we see that the frequency, and this is the apparent frequency. I guess I've got that labeled down here as well, but the apparent frequency, as of course measured in hertz, is going to be equal to the speed of the wave divided by the speed of the wave plus the speed of the source. And all of that is multiplied by the frequency of the force. So the frequency is equal to some factor multiplied by the original source frequency. And this factor depends on the speed of the object. Speed of the source. One thing that I wanted to mention, and I want you to keep in mind when using this formula here, is note that there's a plus and a minus in the formula. So really this is kind of two formulas in one. If the source is moving away from us, well, the frequency is going to have to get smaller, and in order for that to happen, the denominator gets bigger. So our frequency is going to be equal to V over V plus Vs times the frequency of the source. And if the source is moving towards you, then you're going to have to subtract that instead. And your formula sheet has them listed exactly as we've got up here, where it's mentioned both plus and minus, so it's up to you to remember when you have to add them together and when you subtract them. I'm going to look at a couple of examples here, in which case we use this formula to calculate the apparent frequency. A police car that has a kind of an old-fashioned horn with a frequency of 220 hertz. We know that at this location the speed of sound is 340 meters per second, and that the car is moving at 120 kilometers per hour. We're asked to determine the perceived frequency of the sound when A, the car is moving towards us, and B, when the car is moving away from us. So, as always, let's start by writing down what we know. So the first thing that we know here We're told the frequency of the source, we'll use Fs for this, is equal to 220 hertz. We also know the speed of sound, we'll just call that V here, is 340 meters per second. And finally, the car is moving at 120. So the horn is on the car, so that's the speed at which the source is moving, and that's 120 kilometers per hour. We're going to want the same unit for the speed of sound and the speed of the car. So let's convert this to meters per second. We can do that by dividing by 3.6. Remember that little trick, and that gives us a speed of sound of 33.3, or rather a speed of the car of 33.333 meters per second. And we are looking for the apparent frequency, which we're just going to call F. So remember our formula that we have anytime we're dealing with the Doppler effect is that the frequency is equal to the speed of sound divided by the speed of sound plus or minus the speed of the source, multiplied by the frequency of the source. So what do we know here? Well, we know, let me just change colors here. Well, we know the frequency of the source. We've been told that. We know the speed of sound. And we know the speed of the source. So we have everything that we need in order to calculate this frequency, and that frequency is what we're looking for. In this case, we don't even have to rearrange the formula. All we have to do is decide whether we use the plus or the minus. And so keep in mind, so for the first part here, A, the car is moving towards us. So that means we use the minus version of the formula. So frequency is equal to speed divided by speed minus speed of the source multiplied by the frequency of the source. And then it's just a matter of plugging in a couple of numbers. So speed of sound was 340 meters per second divided by 340 meters per second minus the speed at which it's coming towards us, 33.33 meters per second. I'll keep all my digits when I do my calculation here. Multiplied by the initial frequency of the source. And if we do this calculation, we find that the apparent frequency is 244 hertz when it's coming towards us. So it sounds a little bit higher pitched when it's coming towards us than it actually is. Similarly, for part B, it's moving away from us. That means we use the positive version, the plus sign version. So the frequency is going to be equal to, again, speed of sound divided by speed of sound, but this time we're adding the speed of the source multiplied by the frequency of the source. It's a little bit confusing here sometimes because S could conceivably in your mind stand for either sound or source, but in this case it always stands for source. So again, this was 340 meters per second, 340 meters per second plus that 33.33 meters per second multiplied by 220 hertz gives us an answer of 200 hertz. So once it's past us, so if you imagine this car driving along, this is us, we've got a car moving, it's a terrible car, moving that way. Once it gets past us over here so as it's coming towards us, we're going to hear the sound at 244 hertz. Once it gets past us over here, we're going to hear it at 200 hertz. We've got a second example here dealing with the Doppler effect. In this case, we're told the speed of sound in air is 340 meters per second. I'll just write that down. And we're asked, how fast must an object move towards you? So again, that's key, it's moving towards us in order to hear an apparent frequency that is twice that of the source. So this question is a little bit trickier for a couple of reasons. First of all, we are going to need to rearrange the formula this time. Second of all, we aren't actually told what any of the frequencies are. We're just told that the apparent frequency is twice that of the source. And this is something that will often trip people up. The way I think about it is that I would say the frequency that you hear, the apparent frequency, has to be equal to twice the source frequency. And we're going to use this relation to solve our equation. But first of all, we've got something coming towards us. So think about this. Do we use the plus version or do we use the minus version? Well, just like in the last question when we've got something coming towards us, we use the minus sign version, which shows frequency is equal to speed of sound divided by speed of sound minus speed of the source times the frequency of the sound. And in this case, we are looking for the speed of the source. So first thing that we might want to do, and we're going to be doing this sort of in two spots at once, let's divide both sides by the frequency of the source on both sides. So we know the frequency divided by the frequency of the source is going to be equal to 2. We can do the same thing over here. So we can divide both sides, and I'll switch to a different color here. Sometimes that helps. Let's divide both sides by frequency of the source. So that'll cancel out over here. And we are left with frequency over Fs is equal to V over V minus Vs. And again, remember, we're trying to isolate the speed of the source. Trying to isolate. One thing that we can do to make our lives a little bit easier here, so this frequency over the frequency of the source, we said that's equal to 2, so we can just go ahead and replace that. So instead of F over Fs, we know that F over Fs is equal to 2. We're just going to write 2 instead is equal to speed of sound divided by speed of sound minus speed of the source. And so this has simplified down a little bit. Again, we're just trying to isolate this speed of the source. We can multiply both sides by V minus Vs. Which over here on the right is going to cancel out. I'll just take an extra step here. Don't necessarily need to write all these steps down, but sometimes it helps to be sure. Then we're going to have to distribute this 2. So 2 times the speed of sound minus 2 times the speed of the source is equal to the speed of sound. We're getting close now. Couple other things we can do. We can add 2 Vs on both sides. It's going to cancel out. So 2V is equal to V plus 2Vs. Then we'll subtract V from both sides, which again is going to cancel things out. So over here on the left, we have 2V minus V is is equal to 2vs. Almost there. 2v minus 1v just gives us 1v is equal to 2vs. So final step here, in order to isolate for the speed of the source, divide both sides by 2. And so finally, we see that the speed of the source is equal to the speed of sound divided by 2 here. So if we look back at what our speed of sound was, it was 340 meters per second. So Vs is equal to 340 meters per second divided by 2. The speed of the source, in order for the frequency to be doubled here, is going to be 170 meters per second. So this question was mostly about the algebra, which was the tricky part, but keep in mind that we do have to use the minus sign version because the object was coming towards us.